Sigma, Sigma, hey, do you know how a mathematician induces good behavior in their children? If I've told you k times, I've told you k plus 1 times. It's a joke.
All right, Team Rookie here, talking to you about Chapter 9, the principle of mathematical induction. Induction is one type of proof. It's a type of proof that HL Math deals with. I just wanted to list here a few other types of proofs that you may have encountered before. There's a direct proof, something like maybe you've seen geometrical, like two-column proofs or something like that. Basically, you start with a set of principles that are deemed to be true, and then you just go from there. Well, if this is true, then this is true, then this is true, and eventually you get on to what you wanted to prove true. Proof by contradiction is a neat one. You start by assuming something to be true that you're not sure about, and then you just see what happens. And then eventually you arrive at a false conclusion, a conclusion that you know has to be false. And that means that your original assumption had to have been false to begin with. I use proof by contradiction all the time when I play Sudoku and Ken, and I'm not sure what to do in a box, but the most famous historical example I can think of is the proof that the square root of 2 is irrational. You can look that one up if you like. Proof by exhaustion is another one that I thought of, but there's something called the four-color theorem. Says that any map basically can be colored in with only 4 colors, and you'll never have two regions of the same color touching each other. And the original proof of this was actually done with the help of a computer by checking 1,936 different map configurations. It turns out that was all they needed to check. Took over 1,000 hours, but that was the proof. Like literally, we checked all the options, so we know that it's true. And there's lots of other different types of proofs. When I was looking this stuff up, actually, there were proofs I'd never heard of in my life. But these are some of the more popular ones that you might run into with just some introductory university-level mathematics. But induction's the one that we're going to talk about today. The idea of induction, the metaphor that tends to go with it is that of dominoes. So basically, I've got a set of dominoes set up here, and if I were to knock over any one of these dominoes, like if I knocked this one over, then the next one would fall over, and the next one, and the next one, and the next one, and the next one, and so on, and eventually all the dominoes up to the end would fall over. Sounds simple enough. But there's two key steps to this. First of all, I need the dominoes to be close enough together to make sure that if one of them falls, the next one will also fall over. And then also, and this is crucial, I need to actually be able to tip over the first domino. Looks pretty easy in this example, but here maybe not so much. Okay, so these are going to be the steps we're going to follow here. Some people like to use the acronym TAPE, which stands for test, assume, prove, explain. I'm just going to list them out basically here with the domino metaphor next to it. So first step, we're going to show that the statement is true for some specific integer, which is like the showing that knocking over one single domino is possible. And this integer is going to be the first value defined by the problem. So sometimes the problem is going to say for all integers greater than 0. Maybe it's going to say for all integers greater than or equal to 4 or something. It'll be in the problem. Oh, and also for the IB, every single problem I've ever seen has been about integers. In theory, though, I mean, you can do induction for all real numbers and even probably beyond there, although I've never seen an induction proof on complex numbers. We're only going to worry about integers, though. Okay, one big thing about this step. When you do this test, you are going to explicitly state that it's a true statement. It's going to sound very, very obvious. Like you're going to end up with a statement that says something like 2 equals 2, and then you're going to write, which is true. Big deal, trust me. Step 2, we're going to assume that the proposition is true for some number. We'll call this value k. You'll see what I mean about that in just a minute, okay? But we're going to assume that the proposition is true someplace. This is, again, we're like assuming that we can knock over any particular domino. And then we're going to show that if the statement is true for any integer, then it must also be true for the next integer. So if a domino is knocked over, the next domino also gets knocked over. This step is going to involve us using some algebra, and we're also going to use what we assumed up here in step 2 to show that the proposition needs to be true for k plus 1. Remember, we assumed it was true for k, and we're going to show then that it has to be true for k plus 1. And then we're going to write a concluding statement. This is the explain step, and it's basically going to look like this every single time. We're going to say since p sub 1 is true, and p sub k plus 1 is true whenever p sub k is true, p sub n is true for all n greater than or equal to 1. Now, in this example that I just made up, I'm using n is greater than or equal to 1, which means the problem said show that it's true when n is greater than or equal to 1. And since the number was 1, I started here with p sub 1. Had this number been 0, then this number would have been a 0. Those are just going to match. The rest of this is like symbol for symbol verbatim. It's always going to be the same thing every time. Okay, so here's one problem from the book where we're going to prove this particular statement. We're going to prove that 6 to the n minus 1 is always going to be divisible by 5 for every integer greater than or equal to 0. And we're actually going to do this in 2 ways, because why not? Let's review binomial expansion first, and then we'll do induction afterwards. So this is kind of weird that we're writing out the binomial expansion of 5 plus 1 to the n, which is, of course, 6 to the power of n. I've just written it out as 5 plus 1 to the n. Well, let's see if we can use that to show that it's always going to be divisible by 5. So binomial expansion says 5 plus 1 to the power of n is going to be equal to n choose 0 times 5 to the n times 1 to the 0 plus n choose 1 times 5 to the n minus 1 times 1 to the first plus n choose 2 times 5 to the power of n minus 2 times 1 squared plus whole bunch of stuff in between. N choose n minus 1, 5 to the power of, well, it's going to be n minus negative 1, so that'll be 5 to the first times 1 to the power of n minus 1 plus n choose n times 5 to the 0 times 1 to the power of n. That's my binomial expansion. And if I look at these, I notice that every single one of them has a factor of 5 somewhere in it, except for this last one, because that's 5 to the power of 0. But if I were to subtract 1, because that was the problem right there. Wait a second, isn't that exactly what this term is? Isn't this term equal to 1? Because n choose n is always 1, 5 choose 0 is 1, and 1 to the n will also be 1, since n is greater than or equal to 0. So those two terms are actually just going to cancel each other out, and I'm left with a series of terms, all of which have a factor of 5. So yes, 6 to the power of n minus 1 is definitely divisible by 5. Okay, so now let's do this one with induction. So I've started off by rewriting the original sentence instead of in words by just using mathematical notation here. So this says, this is my proposition, p sub n states that 6 to the power of n minus 1 should be equal to 5 times a, where a is going to be some integer. So that's just a mathematical way of saying that it's divisible by 5. And this is going to be the trick for every single divisibility induction problem that you see. And actually, that's the first subtype of induction problems that I'm going to do today. I'm going to do a whole bunch of divisibility ones before I do anything else. They're all going to rely on this use of another letter. I'm going to use the letter A. You can use whatever letter you want, of course, to stand in for that divisibility part. Okay, anyway, and I've noticed here as well that n is greater than or equal to 0. So let's go through the process. Let's start off with this very first value, 0. So I'm going to say p sub 0. What is p sub 0? P sub 0 is going to be 6 to the power of 0 minus 1. Well, what is 6 to the power of 0 minus 1? Well, that's 0. Hey, is 0, excuse me, divisible by 5? Yes, this is equal to 5 times 0. So this is true, and I'm going to say that. I even like to get very enthusiastic and use an exclamation point. So when n is equal to 0, this is a true statement. 6 to the 0 minus 1 is divisible by 5. So that's awesome. Next, I'm going to assume. This is the weird part. I'm going to assume that p sub k is true. And I'm even going to write out that 6 to the k, 6 to the k minus 1 is equal to 5a. And it's like, it's weird because like I just wrote down, this same statement again a second time, just using a different letter. The idea is that n is representing kind of like all values. That's really the variable. K it's a specific value. I know it kind of looks like a variable because it's a letter, but I want you to think of it as just this actual specific value. We just don't know which specific value it is. So anyway, I'm assuming now that this is true. I'm just gonna erase that because it's bothering me. So 6 to the power of k minus 1 is equal to 5a. It's true for whatever this number k is. So let's see what happens when we look at k plus 1. Like what I want to show is that 6 to the k plus 1 minus 1 is also equal to 5a. And somehow I want to get from here to there. Let's see how we can do this. Okay, so the way I'm going to do this is I'm actually going to rewrite this statement here, because that means that 6 to the k has to be equal to 5a plus 1. And this is what's called the inductive step. So I'm going to take this fact and I'm going to shove it into something with k plus 1 to make this be true. So check this out. I might ask myself, like, what is 6 to the k plus 1? Well, 6 to the k plus 1 has to be 6 times 6 to the k. But I know that 6 to the k is equal to 5a plus 1. And if I multiply through, that's 30a plus 6. So if I take 6 to the k plus 1 and I subtract 1 from it, that must be equal to 30a plus 5. And this is obviously divisible by 5. So that's true. And I've done it. And this might feel weird to you at first. The first couple times I saw induction, I definitely was like, what is this black magic you've done? What do you mean that's it? That seems obvious. But it wasn't. It absolutely wasn't obvious. So just a recap here. First of all, I showed that it's true for some number 0. It's definitely true for 0. Okay, you agree. We showed that in the beginning. What I've just shown is that if I assume that it happens to be true at any random place, which we're calling k, if it happens to be true there, then it absolutely has to be true for the next value, k plus 1. So, since p sub 0 is true, and p sub k plus 1 is true, when p sub k is true, look at this handwriting, p sub n is definitely true for all n greater than or equal to 0. Like, it has to be true. Since it's true for 0, this shows that it has to be true for 1. And since it's true for 1, it has to be true for 2. And since it's true for 2, it has to be true for 3. And on and on and on and on and on we go. That's it. It's true. Mathematical induction. Boom, baby! Okay, so let's try to do like 2 more. I'm going to do maybe B and C from this set, okay? So let's do B right now. So we're going to prove that n times n squared plus 5 is divisible by 6. Okay, so my proposition is going to be that n cubed plus 5n is equal to 6a, where a is an integer, for n, which is a positive integer. So that's going to start with 1. 1's the first positive integer. So okay, so we're starting with 1, we said. So p sub 1 is going to be 1 cubed plus 5 times 1, and that's going to be equal to 6a. And hey, you know what? 1 cubed is 1 plus 5, that's 6, and 6 is equal to 6 times 1. Hey, p sub 1 is true. Great news. Okay, next we're going to always write this down. We're going to assume that p sub k is true. That is to say that k cubed plus 5k is equal to 6a. Now, in the last example, I know like it was kind of obvious. I kept the variable term on the left down here in the blue circle, which is now also green. I kept the 6 to the k on the left. I moved the 1 over. Here in this one, it might not be as obvious. Like I've got a k cubed and a 5k. Which one of them should I keep by itself, and which should I move over to the other side? I don't actually have a rule for this. I'm not sure. I tend to just keep the highest power alone. I don't know if that always works. That should be a minus. I think it's going to work here, but I don't know if that's necessarily always the right way. Experiment, find out. Sometimes you're going to have to try something, take a risk in one of these problems and see if it works out. So anyway, we have k cubed is equal to 6a minus 5k, and we're going to use this fact now in our statement about k plus 1, which, you know what, why don't we write down what our target is? Because sometimes you get lost in the algebra and you don't actually know what you're going for in the end, and you might just get stuck and quit. So what do we want to show here? Well, I want to show that k plus 1 cubed plus 5 times k plus 1 is also equal to 6a. And I'm going to have to really be careful with this because this might not look like this in my work. It might actually be expanded. Like I might have to look for k plus 1 cubed in my work, or I might have to look for 5k plus 5 in my work. It's not necessarily going to look like this until I algebraically manipulate it to look like that. Anyway, let's go. And actually, I think I'm going to probably start off with that right away. So like, what is k plus 1 cubed plus 5 times k plus 1? I think I am going to expand that. So k plus 1 cubed is going to be k cubed plus 3k squared plus 3k plus 1. And then I'm also adding 5k plus 5. And now I'm not saying that this is equal to 6a yet. I want to show that this is equal to 6a. Well, what do I know for sure? Well, I have assumed already that k cubed is equal to 6a minus 5k. So I'm free to substitute that in. So instead of k cubed here, I've got 6a minus 5k plus 3k squared plus 3k plus 1 plus 5k plus 5. And we can see a few things are going to cancel out, the minus 5k and the 5k. The 1 and the 5 are going to make 6, so that's cool. So let's see. So I'm going to have here now 3k squared plus 3k plus 6 plus 6a. And I need to show that this is divisible by 6. Obviously, these two terms are divisible by 6, but is 3k squared plus 3k also divisible by 6? That's not as obvious. Well, let's see. If we factor this out, it might be a little bit easier to see. So this is going to be 3k times k plus 1. So I want to show this divisible by 6. Now, if it's divisible by 6, that means that it has to be divisible by 3 and also divisible by 2, right? That'll suffice. This is clearly divisible by 3. Is it divisible by 2, though? Well, yes, because either k or k plus 1 is even, right? Like one of them has to be an even number, one of them has to be an odd number because k is an integer. So that means that 3 times k plus 1 is divisible by 2. It's also obviously divisible by 3, which means that this is divisible by 6. And this is obviously divisible by 6. So we've got it. The whole thing is divisible by 6. And I write my concluding statement once again. P, what do we start with? P sub 0 is true. P sub k plus 1 is true when P sub k is true. So P sub n is true for n greater than or equal to 0. Let me just say a word, by the way, about this concluding statement. This concluding statement is generally worth 1 mark on an IB exam. It's an easy mark to get as long as you score enough points above it. Usually the mark scheme requires you to score, like say it was a 7-point question, they'll usually say, yes, you can get a point for the concluding statement as long as you have scored 4 of the other 6 marks of the question. So you can't just get a free point for writing the conclusion with nothing else. You need to do most of the work above correctly. Sorry. Okay, let's do letter C here. 7 to the n minus 4 to the n minus 3 to the n divisible by 12 for all positive integers. It looks nasty. It shouldn't be too bad, though. 7 to the 1 minus 4 to the 1 minus 3 to the 1. That's 7 minus 4 minus 3. That's 0. And that is equal to 12 times 0. So that's true. You should always be able to get that first step done. That first step should be a free point for every one of you. Okay, we're going to assume, this should also be a free point, by the way. We're going to assume that p sub k is true. So 7 to the k minus 4 to the k minus 3 to the k is equal to 12a, where a is an integer. All right, here, definitely not obvious which one of these we should keep on the left-hand side. It works for 7 to the power of k. I will leave it as a bonus exercise for you to see if you can get this to work out by leaving 4 to the k or 3 to the k alone and progressing from there. Okay, so 4 to the k is equal to 12a plus 4 to the k plus 3 to the k. That's definitely true based on my assumption. Now we're going to use that to say something about our k plus 1 statement, which, by the way, is going to be that 7 to the k plus 1 minus 4 to the k plus 1 minus 3 to the k plus 1 to also be equal to 12 times some integer. So let's see what happens on this left-hand side. What is 7 to the power of k plus 1? Well, that's going to be 7 times 7 to the k, and 7 to the k is this. And then we got to subtract all of this stuff. Okay, well, yeah, all right. Well, let's distribute through it here. It's looking kind of messy, but 84a plus 7 times 4 to the k. That's not 28 to the k. Now, be careful. Plus 7 times 3 to the k minus, here's what I'm going to do here. 4 to the k plus 1 is the same thing as 4 times 4 to the k. And same idea with 3 to the k plus 1. It's 3 times 3 to the k. And if you can come up with that one little step, hopefully the next step is obvious. We're going to combine some like terms. This is 84a plus 7 times 4 to the k minus 4 times 4 to the k is 3 times 4 to the k. And 7 times 3 to the k minus 3 times 3 to the k is 4 times 3 to the k. And it's, oh man, this is like screaming that it's divisible by 12 here, isn't it? So let's factor out a 12 from everything here. Let's see what's left over. 12 from the 84 is going to be 7a. I factor out the 3 and 1 of the 4s, and I'm left with 4 to the k minus 1. And then I factor out the 4 and 1 of the 3s. And there I have it. This is divisible by 12. P sub k plus 1 is true. I write my concluding statement again, which I'm not going to write down, but I will say it out loud. Since p sub 1 is true and p sub k plus 1 is true whenever p sub k is true, p sub n must be true for all n which are positive integers. So that's divisibility. I think that's the last divisibility one I wanted to do. Yes, it is. That's a trick with divisibility. Now we're going to look at some other ones. We're going to look at some that have to do with series. Okay, so now we're going to do a series question. Very similar to what you might see on an exam, honestly. Part A is an induction. We're going to prove that this long series of fractions. By the way, it's not an arithmetic series. It's not a geometric series. It's just a series of fractions that have some special pattern to it. But anyway, we're going to prove that that sum is always equal to n over n plus 1, as long as n is a positive integer. And then we're going to use that. Hence, we're going to find the sum of these fractions. Now, this part B, it seems like something you could do on your own. You could sit there and work out, like, okay, well, what's 1 over 110 plus 1 over 132 plus 1 over... You could do that all the way to 1 over whatever 20 times 21 is. That'd be a lot of fractions to add up with a lot of really crazy denominators to try to work with. And I don't think you'd be very successful. Thankfully, we have this result up here to use to help us. Now, I'm pointing this out because even if you can't do the induction, we can still use this fact from part A to answer part B. So always keep that in mind when you have a hence problem, okay? Even if you can't do the first part, you can use the result that the first part has handed to you to do the second part. Anyway, we'll do this in order now. Let's go. So we're going to prove this statement by induction. Okay, we're starting off with p sub 1 because we're starting with positive integers. So that means now I have to figure out how to write this out. It's going to be just 1 over 1 times 1 plus 1. That's p sub 1. That's my left-hand side for that. How do I know that's right? Well, I'm looking over here at the general term, and I'm saying, well, if n is 1, because that's where I'm starting, n is 1, I'm just going to fill in each of these as 1. And that's the first term for this series. And actually, I mean, it obviously is, since I'm just going to get 1 over 1 times 2, but that's how you should think about it. Anyway, what is that? Is that equal? That's equal to obviously 1 over 1 times 2, which is equal to 1 over 2. And hey, is that equal to 1 over 1 plus 1, which is the format that we wanted over here on the right-hand side? Yes, it is. That's true. All right. Now the induction. So we're going to assume p sub k is true. So that means 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus all the way over here to 1 over k times k plus 1. That should be equal to k over k plus 1. We're going to assume that is true. And now we're going to think about what would happen in the k plus 1th case. The k plus 1th case, well, what is that going to look like? Well, this here, this was the sum of the first k terms. So let's just write out the sum of the first k plus 1 terms. It starts off the same, and that's actually going to be very helpful. It starts off like this, but then I just add one more term, and it's going to be 1 over k plus 1 times k plus 1 plus 1. Maybe you prefer to write that as k plus 2. That's all right. All right, there we have it. Now we need to use what we assumed in here. Well, what we assumed is sitting right here on the left. So I can rewrite that entire chunk as this is k over k plus 1 plus 1 over k plus 1 times k plus 2. By the way, what am I looking for? What do I want? I want this whole thing to look like k plus 1 over k plus 2. Right? I'm just looking at this part here and substituting k plus 1 in for every k. So can I get that to happen? Well, it looks like I'm just going to combine the like denominators here, right? So I need to multiply this one here on the left by k plus 2. And then let's see, what is this going to be equal to? Well, the numerator is going to be k squared plus 2k plus 1 over k plus 1 times k plus 2. And you know what? That numerator is factorable. That's equal to k plus 1 squared, which means that I can cancel out one of the k plus 1s, and there it is. Sorry, that should have been a 2. There it is. We got it. It's k plus 1 over k plus 2. We have exactly what we wanted. It's true. K plus 1 is true. I write my concluding statement once again. Since k sub 1, since p sub 1 is true and p sub k plus 1 is true whenever p sub k is true, p sub n is true for all n which are positive integers. Nice. So now how can we use that induction proof to hence find this sum? Well, you notice if I were to start this at 1 over 1 times 2 and go all the way here to 1 over 20 times 21, that would be like the 20th series sum, right? So like I could call that S sub 20. This would be the total sum from 1 over 1 times 2, adding up everything up to 1 over 20 times 21. Of course, that's not what we're asked to find the sum of here. But it would be if we were to remove the first, well, this starts here at the 10th partial sum, right? So that means that we're subtracting away the first 9. So I have the sum of the first 20 terms of the series minus the sum of the first 9 terms of the series, and that gives me the sum that I want. And I have a formula right here to figure out what each of these are. The 20th partial sum, that's a fancy word for just the sum of the first bunch of terms of a series. That's going to be 20 over 21. And then the 9th is going to be 9 over 10. And I just need to figure out what that sum is. That doesn't look nearly as bad as that other series of fractions did before. Okay, I can do this. I can do this. This is going to be 200 over 210 minus, well, 9 times 21. That's not the easiest thing. 9 times 20 is 180, 189. There we go, over 210. Final answer, I guess that's going to be 11 over 210. Not too bad. All right, so I want to do one more series question with induction, and it's one that you've definitely seen before. In fact, I screen grabbed this from the formula booklet for the course. It's the sum of the first n terms of a geometric sequence. Let's prove this. All right, let's prove this. So we're going to say that p sub n is this. Let's see, what should n be? Let's say n is greater than or equal to 1. Let's start there. Since it doesn't really make sense to add up 0 terms of a series, let's start with 1. So, what's p sub 1? Well, p sub 1 says that the first partial sum should be equal to, well, I guess it's going to be u sub 1 times r to the 1 minus 1 over r to the 1, which those are going to cancel clearly, so that's equal to u sub 1. Is that true? Should the first partial sum just be equal to the first term in the series? Well, yeah, obviously. That's exactly what it is, because we're not adding anything else to it. So that is true. We're going to assume p sub k is true. That is to say that s sub k has to be equal to u sub 1 times r to the k minus 1 over r minus 1. So what can we say about s sub k plus 1? Well, s sub k plus 1, that's the k plus 1th partial sum. Well, that has to be equal to the kth partial sum. So that's the sum of the first k terms plus, what would we have to add to the sum of the first k terms to get the sum of the first k plus 1 terms? Well, we're just missing one term. We're missing the k plus 1th term. So I can call that u sub k plus 1. Okay, so what do we know about this so far? Well, I know that s sub k has to be equal to u sub 1 times r to the k minus 1. Excuse me. Okay, so what do we know about this so far? Well, I know that s sub k has to be equal to u sub 1 times r to the k minus 1 over r minus 1. Is there another way that I could write u sub k plus 1? I mean, this is a geometric series, right? So any particular term can always be related back to the very first term by multiplying it by enough factors of r. So let's see, in this case, if I wanted to get the second term, I'd multiply the first term by r. If I wanted to get the third term, I'd multiply by r squared. So if I wanted to get the k plus 1th term, I'd have to multiply by r to the power of k. All right. Ooh, this is looking interesting now. Let's simplify. So this is going to be u sub 1 r to the k minus u sub 1 over r minus 1 plus, I'm going to have to combine these in a second anyway. Let's just do it. R minus 1 times u sub 1 times r to the k. Let's just make that all one fraction. Now, let's simplify. Okay, so this is u sub 1 r to the k minus u sub 1 plus r to the k plus 1 u sub 1 minus u sub 1 r to the k all over r minus 1. Let's see, what can cancel out now? Well, I have u sub 1 r to the k minus u sub 1 r to the k. Great, great, great. Ooh, and I think now if I just factor out a u sub 1 from both of those terms, I will have r to the k plus 1 minus 1 over r minus 1. And that, I didn't actually write out my target just now, but that is exactly what I would have wanted this to look like. Should be u to the u sub 1. This is going to be r to the k plus 1 minus 1 over r minus 1. That's exactly what we have there. Geometric series, finite geometric series sum, proved by induction. All right, the next type of induction we're going to look at are inequalities. They're a little weird, and I have to warn you, typo alert, typo in our textbook. Exercise 9b.3a, number 2a should read 3 to the n is greater than or equal to 1 plus 2 times n. So we are going to fix that in our screenshot from the textbook right now. Okay, let's do it. We're going to start. Okay, and this is, by the way, n has to be a natural number, which in the IB means n is greater than or equal to 0. So p sub 0 is 3 to the power of 0 is greater than or equal to 1 plus 2 times 0, which is, of course, equal to 1. Is 1 greater than or equal to 1? Yes. That's true. And you can see if that hadn't been greater than or equal, that would have been false. Of course, we could have changed this from natural numbers to just being positive integers, and that would have solved it. But anyway, let's move on. So we're going to now assume p sub k is true. That is to say that 3 to the power of k has to be greater than or equal to 1 plus 2 times k. All right. We want 3 to the k plus 1 to be greater than or equal to 1 plus 2 times k plus 1. I'm going to try to find that somehow. Let's see what we can do here. So 3 to the k plus 1, what is it? 3 to the k plus 1 is 3 times 3 to the k. 3 times 3 to the k. Well, 3 times 3 to the k has to be greater than or equal to 3 times 1 plus 2k. Where is this coming from? This is coming from right here. I'm using my assumption that 3 to the k is greater than or equal to 1 plus 2k, and I'm just multiplying both sides by 3. That's allowed. From here, let's see, this means that 3 to the k plus 1 is greater than or equal to 3 plus 6k. Gosh, how am I going to link that to this part here? Well, let's rewrite this. Let's actually expand that for just a moment. That's going to be 2k plus 3. So that's 2k plus 3. But in our work, we've got 6k plus 3. Well, think about it for just a second. I mean, isn't 3 plus 6k greater than or equal to 3 plus 2k? Doesn't that have to be true? because k is a positive integer. So obviously 6 times k has to be bigger than 2 times k. Yeah, it is true. So look at that. It's done. It's done already. All I have to do is think a little bit flexibly about what I'm allowed to do with an inequality, and we're good. Concluding statement. Since p sub 0 is true and p sub k plus 1 is true, whenever p sub k is true, p sub 0 is true. Excuse me, p sub n is true for all n which are natural numbers, or for all n greater than or equal to 0. That was pretty cute, right? Let's try the other one now. So let's try this other one now. So let's try this other one now. And oh my gosh, not only does it have an inequality, it has factorial in it. This is going to be amazing. And this one's actually starting with kind of a weird choice. It's starting with n greater than or equal to 4. You don't see that every day. Let's go. So p sub 4 says that 4 factorial should be greater than or equal to 2 to the power of 4. Well, 4 factorial is 24. 24 is greater than or equal to 16. So p sub 4 is true. And we're going to assume that p sub k is true. P sub k is going to say that k factorial is greater than or equal to 2 to the power of k. All right. We want k plus 1 factorial to be greater than or equal to 2 to the k plus 1. Let's be on the lookout, see if we can make that happen. So what is k plus 1 factorial? Well, k plus 1 factorial is equal to k plus 1 times k factorial. K plus 1 times k factorial has to be greater than or equal to k plus 1 times 2 to the k. Again, I'm using the assumption up here. I'm just multiplying both sides by k plus 1. Since k is a positive integer, k plus 1 is also positive, so my inequality does not change directions. From here, what do we have? Well, now we just need to show, since I've got the k plus 1 factorial here on the left, that's bigger than this. Is it true that k plus 1 times 2 to the k, is that greater than or equal to 2 times 2 to the k, which is 2 to the k plus 1? Well, yeah, k plus 1 is definitely bigger than 2 because k has to be bigger than or equal to 4. So k plus 1 is at least 5. So this is definitely true. My inequality is true again. I did it. The inequality ones are fun for me because they're actually some of the easiest ones if you just think to do this one little thing. But if you don't think of it, they're actually really hard. Anyway, since p sub 4 is true and p sub k plus 1 is true, whenever p sub k is true, p sub n has to be true for all integers greater than or equal to 4. So that's inequalities. And now I just wanted to share with you two examples from, just one example from a previous HL math exam. This is from 2017 May, time zone 2. It's question number 8. And it's an induction problem with binomial expansion. Okay, so this is a 9-mark question. Let's see how we do. We're going to start off with 3, right? So p sub 3 says that, hang on, now I got to think again. How many terms should I use here? Do I use the first 3 terms? Is that what it means? It started with n equal to 3? No. No. We're going to start off with the first term here. It's really just 2 choose 2. It's really always going to be the first term when it's a series. But if you're not sure, again, just look at your general term here. We're starting off with n being 3. When n is 3, this turns into 3 minus 1, which is 2 choose 2. And that's the first term of the series. So 2 choose 2. Is 2 choose 2 equal to 3 choose 3? Yes, that is true. They're both equal to 1. So p sub 3 is true. And we're going to assume p sub k is true. P sub k says 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus ... to k minus 1 choose 2 is equal to k choose 3. Let's say something about k plus 1 then? Well, the k plus 1th sum, just looking at the left-hand side, is going to be same thing. 2 choose 2, 3 choose 2, 4 choose 2, k minus 1 choose 2, and then the next term is just going to be k choose 2, right? Because it's k plus 1 minus 1. Choose 2, and let's see, well, what is that equal to? Remember, what we want is for this whole thing to be k choose 1, choose 3. We would love to see that pop out of this. Well, I know that this part is equal to k choose 3 by my assumption. So I'm going to add k choose 3 with k choose 2, and let's see what happens. For this, we're going to actually use the definition of what k choose 3 is. K choose 3 is going to be k factorial over 3 factorial times k minus 3 factorial. Add that to k factorial over 2 factorial times k minus 2 factorial. All right, so we're going to combine these two. Finding a common denominator might not be obvious at first, but my common denominator is going to be 3 factorial times k minus 2 factorial. That's it. Why is that? Well, because 3 factorial is 6. So 6 already has a factor of 2 in it. And k minus 2 factorial is k minus 2 times k minus 3 factorial. So it already has a factor of k minus 3 factorial in it. So that means that I need to multiply this left-hand term by k minus 2 and my right-hand side by 3. Okay, let's see what comes of this. This might be a good time to notice that since I've rewritten these factorials on the left into, the choose notation on the left into factorials, I might want to rewrite this guy into that notation as well. So I'm now looking for k plus 1 factorial over 3 factorial times k plus 1 minus 3 factorial. And look at that, the denominators match. The denominators match already, so I just need to show that the numerators are in fact the same, and I'm good to go. So that's why I write the target down. Always good to refer back to that if you're at any moment you get lost. Because at this stage right here, like, you could definitely be uncertain of yourself. Like, man, I got to get from that to something that looks so simple, like this over here. I mean, come on. So just, use your algebra, use your formula sheets. Keep a cool head. It's going to be all right. Okay, so let's just combine our numerators now. So on the left, I'm going to have, this is going to be k times k factorial minus 2 times k factorial plus 3 times k factorial, which is going to be the same as k times k factorial plus k factorial, which is the same thing as k factorial times k plus 1, which is k plus 1 factorial. So the numerators match as well. I've done it. It's true. I write my concluding statement. Since p sub, where did we start here? 3. Since All right, so I p want to sub close 3 this is off true, with just and one p sub k plus nonsense 1 example. Is One true place where whenever p sub induction k is true. can go P sub n terribly is true, wrong if for you're not all careful n and you don't follow greater all the than steps. or equal to 3. I would like to prove that n plus 1 is less than n for all n greater than or equal to 0. Obviously, this is false, right? I mean, we know this isn't true, but let's just go through it here. Let's skip the first step for just a moment. And let's just begin with the assumption. Like, what if we just focus on that? So let's assume that k plus 1 is less than k. Let's assume that was true. Remember that we want to show then that k plus 1 is less than k plus 1. Well, I mean, this follows directly from the assumption. Clearly, if I just add 1 to both sides of that inequality, that I reach the desired statement. So this here is an inequality that if this was true for any number, it would definitely be true for the next number. It absolutely would. If I could push over the first domino, the rest of them would fall over. The problem is, this is a Stonehenge set of dominoes. There's no value that this statement is actually true for. Obviously not. So because it's not true anywhere, it doesn't matter that if it were, the next value would be true, because the fact is, it's not. And that's why we really need to show and state in the very beginning that our initial test value is true. Okay, so just to recap the steps there again, we're going to test a particular value, which is really going to be given to us in the question. They'll tell us what the first number should be. It should be obvious. We are then going to assume that it's true, and we're going to use the letter K for that assumption. We are then, this is the hard part, we're going to prove that it's true for K plus 1. We're going to use algebra. We're going to use our assumption to get there. If you do not use your assumption, you've done it wrong, I guarantee it. And finally, we're going to explain. That's going to be our written sentence, just concluding the problem using the template that I gave you earlier. Test, assume, prove, explain. That's mathematical induction. Honestly, once you get into a groove with these and you start to get them, it's just simple algebra is all you need to work out, and the rest of it just falls into place, and it's actually really nice.
So now you know what to tell those idiot friends of yours who say stupid things like, don't you know what happens when you assume things? Yes, I do. I prove them by induction.